In this video, we're going to go over oxidation and reduction of aldehydes and ketones. So, just a little review about organic oxidation in particular. In organic oxidation, what we're really doing is increasing our number of carbon to oxygen bonds. Now, when we do that, we are at the same time decreasing the number of carbon to hydrogen bonds that we have as well. So this is particular to organic oxidation. Organic reduction reduces your number of carbon to oxygen bonds, while at the same time making more carbon to hydrogen bonds. So we don't focus so much on individual electrons and losing electrons and gaining electrons. We tend to focus on the number of carbon to oxygen bonds in particular for organic oxidation and organic redox. Okay, so to review, what are our strong oxidizing agents? Sodium dichromate, potassium dichromate, Na2Cr2O7 or K2Cr2O7. That Cr2O7 is the dichromate polyatomic ion. So that is a particularly strong oxidizing agent, but it's pretty nasty. It is able to oxidize primary alcohols to aldehydes and then ultimately to carboxylic acids. So primary alcohols get all the way to carboxylic acids with a strong oxidizing agent like dichromate. It will oxidize secondary alcohols to ketones, but it cannot oxidize tertiary alcohols. So tertiary alcohols will not undergo any oxidation with dichromate. Now, weak oxidizing agents like Benedict's and Tollen's reagent, they are able to oxidize aldehydes to carboxylic acids. So that takes an aldehyde to a carboxylic acid. Ketones in general are quite resistant to oxidation, particularly with these. Dichromate and Benedict's and Tollen's will not be able to further oxidize a ketone. When we think about a ketone has two bonds to that C double bond O, and it has bonds to carbon on either side. So it doesn't have a bond to hydrogen that would allow it, like an aldehyde, to be able to be oxidized. So they're pretty resistant. Doesn't mean that there aren't some reagents for it, but these will not do the trick. And then we can reduce ketones and aldehydes, reduce them back to alcohols with hydrogen and nickel for a catalyst. Now, we learned that this catalyst can be used to take an alkene, so a CC double bond, and react with it, right, and add hydrogen across the double bond. When we used a metal catalyst, we were able to break the double bond and make a single bond, and we were able to go ahead and add hydrogen across that alkene and convert it into an alkane. So we've used, this reducing agent before. We've used this reactant before, or reagent set before, but we're just going to use it a little differently here. Here, this reagent can take a ketone. So we've got our C double bond O, and we're bonded to carbons on either side, and can reduce it back to an alcohol. So then our C is going to be bonded to an O and an H, and it'll bonded to C's on either side, but it will have to have a hydrogen right here. And so it's a reduction because you'll have this one more bond to hydrogen and one less bond to oxygen. Same with aldehydes. An aldehyde would have C double bond O, and then a carbon on one side and a hydrogen on the other. And again, we can use our hydrogen with our nickel. Use our hydrogen and our nickel that should be an H, to make our alcohol. So we'll have Our carbon will still have a bond to carbon, and it'll have one bond to hydrogen like it did before, but it'll have one more bond to hydrogen. So again, we have more bonds to hydrogen in reduction and less bonds to oxygen when we're using that reducing agent. So let's look at some example oxidation and reduction of aldehydes and ketones. So first we've got CH3CHOH. So since our OH is just bonded to one carbon, this is a primary alcohol. So we've got a primary alcohol, and we're going to use it to review oxidation a little bit. We're going to write our strong oxidizing agent just as a bracket and an O in brackets to show that we've got a strong oxidizing agent. This would be something like, sodium dichromate, Na2Cr2O7, for example, could be our strong oxidizing agent. And we could use that to oxidize our primary alcohol. In this case, it's got two carbons, so it's ethanol. We can oxidize that to an aldehyde. Oops, I didn't actually want to draw this bond to hydrogen. I just meant to make an aldehyde. So we can oxidize that to an aldehyde, but a strong oxidizing agent will further oxidize this. So I have my two carbons and my CH3, and will further oxidize my aldehyde to a carboxylic acid. So we have our primary alcohol, ethanol, goes to an aldehyde, and then it's oxidized, so O in brackets, further to a carboxylic acid. Now, if all we wanted to do was take an aldehyde and oxidize it to a carboxylic acid, and we're just trying to do that second step, we could use a weaker reagent like Redox, or we could use our toluenes. Either of these would do the trick to just get the aldehyde to the carboxylic acid. Now, you can go and reverse these. You can take a carboxylic acid back to an aldehyde. We just put an H in brackets if we're going backwards to say that, hey, this way is reduction. So the O in brackets was really telling us that it was oxidation. But we can go backwards from our aldehyde back to our primary alcohol with a reducing agent. So like H in brackets to reduce that. So we were saying that aldehydes and carboxylic acids can undergo reduction. Okay, let's take a look at our next example. We've got CH3, C with an H, C connected to CH3, and that middle C with an H is connected to an OH. Since it's a middle carbon with carbons on either side of it, on the two sides, that's a secondary alcohol. So let's look at oxidation and review oxidation of a secondary alcohol. We can oxidize a secondary alcohol to a ketone. So that'll be CH3. And then this middle alcohol C will oxidize to a ketone, and then another CH3. So we have one less bond to hydrogen here. We have one more bond to oxygen. We have a double bond. This can't undergo any further oxidation. You can't further oxidize a ketone to anything else. That carbon is maxing out its number of bonds, and it already, it's maxing out its number of bonds. We already got rid of the only hydrogen we could. It can undergo reduction in the opposite direction. We'll put a little H in brackets to go backwards for our reduction. And so our ketone, much like our aldehyde or carboxylic acid, could be reduced. In this case, our ketone will be reduced back to our secondary alcohol, rather, and we could use our hydrogen and nickel for that. Now, in our last example, we have CH3, C, CH3, and connected to that middle C is a CH3 and an OH. So this middle carbon, there's a middle carbon with 3 CH3s coming off of it and 1 OH. Since that middle carbon is connected to 3 other carbons, it is a tertiary alcohol. Okay, and so as such, it doesn't have any hydrogens to be lost in oxidation, any bonds to hydrogen in that, connected to that center carbon. The carbon with the OH, again, doesn't have any hydrogens. So this really cannot undergo oxidation. So it doesn't matter if you try to give it a strong oxidizing agent, there'll really be no reaction here. Because that central carbon doesn't have any hydrogens on it to be reduced. So there's no reaction there whatsoever. So tertiary alcohols can't be oxidized. When we're thinking about our new reactions of aldehydes and ketones, we're really looking at the fact that we can take these oxidation reactions backwards in terms of reduction. So again, we can take our ketone, we can use hydrogen and a nickel catalyst and reduce our ketone back to a secondary alcohol. We can take our carboxylic acid or our aldehyde and reduce these with hydrogen and a nickel catalyst back to a primary alcohol. So again, that hydrogen and that nickel or that metal catalyst that we have used to hydrogenate an alkene can actually be used to reduce carboxylic acids or aldehydes to primary alcohols and can be used to reduce a ketone to a secondary alcohol. So here's a couple more examples. Let's take a look at the first example. We've got CH3, CH2, CH with a CH3 group coming off of it, and then CH2, CH2, and it ends in C double bond O H, so it ends in an aldehyde. And then we've got Na2Cr2O7. So we should recognize this as dichromate as a really strong oxidizing agent. Now, we're going to copy the whole molecule all the way to the aldehyde because the carbon chain is not going to be changed by oxidation. So it was CH3, CH2, CH, CH3, CH2, CH2, and then we're going to oxidize this aldehyde. So we're going to oxidize it to the carboxylic acid. So we'll have C double bond O, and then we'll have O and H. Sorry, I almost ran out of room there. But we're going to take that aldehyde with our strong oxidizing agent. So we recognize it as an aldehyde because it's C double bond O with an H. And then we're going to oxidize it to the carboxylic acid with that strong oxidizing agent. Okay, let's look at the next one. We've got a line angle formula, but it's essentially like line, 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 and then it's double bonded to oxygen. And then we've got a group coming off of that second carbon and a group coming off of that third carbon. 1 carbon groups each, so some methyl groups coming off of there. So again, we're going to see it reacting with Na2Cr2O7, a strong oxidizing agent. So we're going to just copy the carbon chain verbatim because nothing is going to change about it. What we want to notice is at the end, there was a C double bond O with an assumed H here at the end. And with a line angle formula, you kind of have to assume the right number of H's are there, even when they're not drawn in. So what we're going to do is, again, we've got that C double bond O with an H, or we've got that aldehyde. We're going to oxidize it to a carboxylic acid. So we copy the whole molecule, copy all the carbons and hydrogens that we've got, and then we take our C double bond O with an H and change it to C double bond O, OH. We change our aldehyde again to a carboxylic acid, and we make sure that we don't change anything else about it. We're copying the rest. Okay, then we see we've got another example, CH3, so there's 3 CH3s on a C. Then there's a C double bond O. Then there's CH2, 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 CH3. So what we notice is that a C double bond O is in the middle of carbon chains. So that is a ketone. We're reacting this with Na2Cr2O7. Our sodium dichromate, our strong oxidizing agent. And we're trying to oxidize a ketone. Now, to do that, we'll have to have more bonds to oxygen, but that central carbon already has a double bond to oxygen and 2 bonds, bonds to carbon on either side of it. So it doesn't have any C to H bonds to get reduced or to rather get oxidized to C to O bonds. It doesn't have any C to H bonds to change over to C to O bonds and get oxidized. So we can't do this. This one's a no reaction, right? Because ketones are not going to be oxidized by our sodium dichromate oxidizing agent. So aldehydes get oxidized by sodium dichromate, ketones do not.